Okay, hello everybody. So today we will start the first lecture of mixed signal VLSI design for spring semester 2011, and just let's start. Okay, so today is an introductory lecture. So we will talk about what are the prerequisites, content of the course, references, which CAD tools and technologies we will use in this course, and what you will learn. Accordingly, you will be graded. Whatever is related to CDIP, because this is a CDIP course, therefore we should obey a few rules. And finally, I will start talking about modern network synthesis theory, which is the basics of the first part of the course. Okay, so prerequisite is CMOS analog VLSI design that I am sure all of you have taken. Is there anybody who has not taken 618? Okay, can you tell me why? But that is fine. But you knew this is the prerequisite. It is given in the timetable also. So you can drop the course, you take it next year. Okay? You can sit through if you want, no problem, but you drop it. Okay? So those who don't have EE 618, because it's not, I have written simultaneously because there are some remote centers may have similar course, similar to EE 618, therefore they can take it simultaneously. But if you have not taken here, therefore you can sit through, no problem. Don't audit the course, just you take the course next year. That is absolutely fine. Okay? As far as learning is concerned, you will learn whatever you need. So what are the content of the course? We will have a review of continuous time filters, because this is the basic and backbone of many systems and circuits that we will make in this course. And then discrete time filters based on continuous time filters, basics of analog and digital, analog to digital and digital to analog converters, and then different architectures of converters. Okay? And then a little about what are the points related to a mixed signal layout, and a little about now how we should test analog and mixed signal ICs, what are the points we have to consider, because this course is not only a theory. Students who attend this course are supposed, at least half of them, to contribute in the projects which deal with directly chip fabrication, and therefore it is good to know few of these points. And then a little about interconnects, DLL and PLL, and finally we conclude the course. So this course has many references, and I have tried to specify references which are available in here, and then you can easily access them. I strongly recommend you purchase books. Don't rely on borrowing from library. These books are Indian editions, therefore prices are not very high and they are affordable to all students. And even if you have some priorities, put purchasing books on the top priority. Therefore, you can save money from others. Okay. So, latest edition of CMOS mixed signal circuit design by Baker, 2008. Design of analog MOS circuits by Behzad Razavi, which was one of your references in EE 618. CMOS circuit design layout and simulation, again by Baker. Revised second edition 2008 is available. I'm not sure if Indian edition of this edition is available, but if it is available, you purchase. And there is another book again by in Indian edition version by Rudy, CMOS integrated ADCs and DACs. That is also a useful reference. And then there is an old filter design handbook, which is a very nice book from Arthur Williams. These are additional references, means that you may not deal with these references a lot throughout the course, but you may, specifically at the beginning, you will need to use this book. This book is not available out of stock because it is an old book. It's available in library, 1 volume only, and that is with me. But don't worry, I will return it till Friday. However, don't borrow that book from library. Keep it as a reference in the library, and then all students can use it in the library. Because when I give you, for example, a small project, then you need to use that book to get values. And those values, of course, might be available from net. If it is not, still you can use, because that's a handbook. You can get value of components, or you may get, for example, order of polynomial. Usually you get order. It doesn't have value of components as such, but when it is available, you can just use it, and then in your project refer which page of Williams' book you have used. And worst case, you just take a Xerox copy, just one page, okay, in the library, and attach it to your project report. Therefore, that's enough, okay. So don't borrow that book. And there is another book by Shoman. I don't follow exactly the technique which is given in Shoman book for conversion of continuous time to sample data. There are reasons for that, because there are easier methods compared to that. However, that's a good reference if you want to have more, in fact, insight into the design of analog filters or continuous time filters. And for test, you can use reference 7, which is again Indian edition, therefore it's available. And then we will use several papers. I will give you papers, means that I will specify title of papers and where they have published. Those papers will be used for doing mini projects. So in fact, you will reassemble the circuits which are given in the papers as mini projects. We don't have something called assignment in this course. All assignments will be in the form of mini projects. We don't have a big project at the end of this course, because I believe NSEM project clashes with NSEM exams, and the best thing to do a project is to do it in 4 months. So therefore, you will have several mini projects instead of assignments. For CAD tools, I don't force you to use a specific CAD tools. I recommend to use Vector or Cadence. You can use also HSPICE and Synopsys Flow, which are available. However, whatever tool you will use, you will do the entire flow using that tool. So you may also, if there is limitation of licenses, that I don't think will be the case, you can do, for example, some simulations in one tool and then some other simulations in another tool. That is also fine, provided there is consistency between them. Okay. We will follow custom IC design flow, but without layout. If it is required, we will enter into layout. But we may also go with ASIC design flow. That is not still conform. I need to conform it with Professor Desai. The last interaction I had with him, he said it is ready. So because it's a mixed signal design course, then we may also have ASIC design flow. Therefore, you will follow 2 flows in this course. We will use 0.18 micron UMC CMOS process only in a limited fashion, because these are all foundry models. Therefore, we will use only in a limited fashion, and you are not supposed to disclose any content of the model file. Only you will report your assignments or mini project, and then you don't refer to any model parameter in your project report. So, grading, because it is the only way that we can talk about whether we learned some course or not. See, as you can see, there is no assignment in this grading. So assignment is for your learning. So I believe you are at the level that I should not give you assignment. Any book you look, textbook has many problems. If you, as a interested student, don't touch any assignment throughout the course, that means that really you don't have that passion, honestly. If you have passion, without me to force you, you will do it. Therefore, because it's a PG course, and this is in fact again on top of a core course, therefore it's better to do all assignments in the form of projects. Therefore, combining 2-3 assignments in one project will be the content of the course for evaluation. There will be surprise quizzes. The reason is I have found this method very effective because always you will be with the class. You will be always prepared. So therefore, I don't announce any quiz. So quiz always will be a part of the lecture. And that is good because if I want to tell you something, I will give you in the form of a quiz in a simplified version, of course. And then when we solve it in the class, so this is just like a example for something that you have learned before. So I have kept Mondays 12 to 1 p.m. only for this course, only 1 hour. Therefore, you don't come at 1:55, right? So 12:55. So 12 to 1 p.m. means that in this duration, I will try to keep everything aside. If you have some doubt that takes a lot of time in the class to discuss, you can come around 12 o'clock. So we can discuss and then we'll be over by 1 o'clock at most, right? All interactions will be through model. So one is office hours and one is interactions through model. So these two will be very helpful. Specifically, it's a very nice forum platform. So one of you can, for example, post a question and others can answer the question. And then if again there is a query or objection so on one of the questions, then again there, and then this works very well. And even you are okay, you are quite free to interact about your projects on model. That is encouraged even, no problem at all. That is much better than copying each other. Okay. And there is no information on EE website, only it is used for grading. Okay, so I don't use model for grading, so it will be only on EE website. But all technical parts will be, and everything else, announcement, everything will be through model. So several rules we need to obey. First of all is, we cannot have many questions time to time, but every 10 minutes, 15 minutes, I will tell you, like, if you have any question, you can ask. And I should repeat your questions, therefore if I forget, please just remind me. I try to write with large font size. Sometimes I lose the control, but this is something that we should get used to. And because I need to switch between camera and switch between laptop and paper pad, so therefore if this doesn't happen properly, you tell me. Sometimes it has happened, I just imagine it is done and then I continue, and then after 10 minutes then the student said, we don't see anything. Okay, so there, till this point, is there any question? So if you ask a question, as long as I know it, and then as long as it is short, I will answer you. If it needs more discussion, then you come in on Monday, and then every Monday we will discuss it more. And I think overall this should be an interesting class for all of us. Okay? So first I switch to papers. The reason I don't use many slides is because then it will be like a seminar and the concept of learning will be lost. But when you write, then you will learn. Therefore, don't consider I will keep everything on model. So whatever I show here may not be shown on the model always. Otherwise, it is like a cooked food and then you will just eat it. So you should also participate in cooking the food. Okay? So therefore, don't think I will spend time, will prepare nice slides, and then will keep there, and then you will copy it, and then that will be the course. This is not, this won't work. This will work very well when there are remote centers, when there is no live classroom. But when there is live classroom, let's make it with more interaction. And of course, even for remote centers, I prefer always to have some writing material that when they listen, they will also write. When you write, you will learn. In design, if you don't write, means you don't learn. So this is the stop. So now I will switch to this. So first is a review of continuous time filters. So why do we need continuous time filters or analog filters? Because all signals from nature are analog. Therefore, to capture signals from nature, we need to have an analog platform. But there are many problems with these signals in the nature. These signals are mixed with noise. These signals have a limited frequency band. These signals are not very high. And always there are different types of interferences on these signals. Now, if you want to make an electronic system which will acquire signals or will send signals somewhere else or will transfer them through a media, which can be even a wire, or it can be another media, or it can be through air. So now, suppose you have a system which captures signals from nature. So after acquiring the signal, you need to condition the signal, remove noise, amplify the noise, and to limit it, therefore you need to limit it to a particular bandwidth in which you have enough information. So therefore, to do that and limit it to a particular bandwidth, which is useful bandwidth of the signal, therefore you need some sort of filtering. This filtering therefore need to be done in analog domain. How you can convert a signal to a digital while it is not filtered? Therefore you are converting signal along with noise to a digital form. But your SNR or signal to noise ratio should be enough high before conversion to digital. Because digital itself adds quantization noise. And if your signal has already a lot of noise, therefore how you can do it? So filtering is a requirement. At least till today, technology is in such a way I need analog filtering. Who knows about tomorrow, but at least today is like that. If tomorrow something changes, then we will talk only about digital filters, no problem. So now, before starting about continuous time filter, we need to make sure that when we deal with analog signals, so today's content of this course is Introduction to Modern Network Synthesis Theory. Okay, the first part of this course. And it is based on the very well established old network theory, and it will cover two parts. One will be properties of driving point impedance and canonical forms of RLC networks. So we will reach to that, don't worry about it. But before that, one thing which is very important in analog circuits or even mixed signal, because in mixed signal systems, at the beginning or at the end, you will have analog signals. It's very important always to be cautious about noise. Why we should be cautious about noise? I don't enter into the concept of noise. You know it already. You had E618. So you know that a resistance has a random thermal noise. Therefore, even if I use the simplest component that I can use, resistor, it will have a noise. Now, if I have some sort of noise, any sort of noise in my devices, then when I use analog signals, I should make sure that my analog signal level is above level of noise. For example, at least 10 times more, right? And to become 10 times more, then this means that I have a limitation on the minimum signal level. that I can have in the system. But if you put a limitation on the minimum signal level in the system, then means that you cannot have a desired range if your supply level is limited. So to increase this range, you always like to operate as high as possible and as low as possible in the amplitude domain. So this means that if I have an analog signal, I would like to be free to reduce this signal level as much as I want and increase it as high as I want. But this is not practically possible. And consider this is absolute value of the signal. So therefore, this is, for example, some level which is my threshold level. So I call it X mean, and there is an upper limit. I call it X max. X max is usually determined by linearity of the system, and X mean is determined by the noise of the system. If there was no noise, then ideally we could operate with signals as low as picovolt, picoampere, right? And any other quantity, physical quantity. And if everything was perfectly linear at any level of voltage, we would be able to, of course, forget about breakdown and other reliability issues. If everything was perfect, there was no nonlinearity, I would be able to operate my system at least as long as breakdown and reliability issues permit at high voltages. So therefore, one thing first of all in designing any system, including this networks, is to consider always there is a dynamic range. So these are all basic concepts that we should keep in mind when we design a circuit. So you know, this is because we want to enter into the network synthesis theory, this is a very simple network, a low pass filter. So I'm showing in Laplace domain. So we need to have an idea really how this system limits me. For example, if somebody tells you what is the range of input voltage which can be applied to this simple RC filter, you may say that okay, any value, right? Doesn't matter. But actually it matters. You cannot apply any signal to this RC circuit. There is a minimum value and there is a maximum value. You know, power spectral density of noise in a resistor is 4 kB T into R. F for frequencies above than 0. If you make it 2, then it will be for all frequencies. This is a constant value because you know power spectral density of noise is flat, means that thermal noise essentially is a white noise. We don't have any ideal white noise practically. However, we can approximate it at least in the range of frequencies we deal with. So therefore, it will work at least in the content of this course. Thermal noise of a resistor will be white. So Kv is Boltzmann constant. Which is equal to 1.38 into 10 to the power minus 23 joule per degree Kelvin. And T is absolute temperature versus degree Kelvin. So therefore, power spectral density of thermal noise is flat for all frequencies. Okay. Now, to get an idea, for example, if you have a resistor of 50 ohm, just an example, I say 50 ohm because this is one of the standard values which is used in many RF systems. So at room temperature, which is 300 degree Kelvin, effective RMS value of noise will be 0.91 nanovolt at 1 Hertz bandwidth. Okay, so because this is power spectral density, and from noise background that you have already, you know that if it is white, then it's very easy because to calculate RMS value, because you need just to take the integral of area for a 1 Hertz bandwidth, and because noise density is constant, therefore it will be same as PSC at 1 Hertz bandwidth. Okay, so therefore now we have this noise, and then now we have a low pass filter, completely passive filter, and we think it is an ideal filter, therefore we can apply any signal. Now we need to see what are limitations on simple RC filter. So now we convert S to J omega, and we will go to the J imaginary axis only. So we will write transfer function. Okay, so magnitude will be one upon RC omega square, and the phase will be minus tan inverse RC omega. Okay, so it is very simple. Now we have a noise in the system, right? Inherent noise. Therefore, I connect input to ground. This is source of noise. I show it as a series noise source with resistor and then a capacitor. Okay. So therefore now, even if I don't have any signal, I will see some noise in this system. So what is value of this noise? So then here, this noise source has a flat power spectral density. However, filter is not flat. Therefore, output voltage of this system now will have a non-white, in fact, spectrum. So, in other words, power spectral density is not constant across all frequencies, and it reduces as I increase frequency. So, you know this relation is valid for linear systems. This is PSC at input, and this is PSC of noise at output. In other words, if you have a power spectral density of S in F at the input, power spectral density at the output will be S in multiplied by the square of magnitude of the transfer function. Okay, so we will use this, and then accordingly we can get the power spectral density and accordingly noise at the output. Okay, so I consider the whole range of frequency from 0 to infinite, and then see, because as frequency increases, this level reduces, therefore this integral won't be unlimited. But if you have a single resistor, practically, ideally, if you want to derive RMS noise for a complete range of 0 to infinite, it will be infinite value. But here it won't be, okay? Because there is a reduction in the power spectral density of noise at the output due to filtering. So this was PSC of noise at the input. This is a square of magnitude, and then I integrate it. Okay, so therefore this will give me, I am integrating for the whole range, therefore this will give me average value of square, right, which is in fact RMS square. So therefore how much noise I will get at the output? So we will calculate it. So you know, this essentially gives you this tan inverse x. Therefore this part is constant. Therefore if you calculate, final value will be kT by C. And that is that famous kT by C noise. So therefore, you cannot apply any signal. The signal you apply should be at least 10 times above this RMS value. In other words, RMS value of the signal at the input should be 10 times of this RMS value. And this RMS value is completely inversely proportional to, RMS square is inversely proportional to 1 upon C. That's why using larger capacitors leads to less noise. That is very important. For example, in sample data systems, you may need to use larger systems, larger capacitor exactly for the same reason. So and interestingly, it is independent of R. So intuitively also you can see the reason is because if you increase R, then RMS value of noise in the resistor increases. However, at the same time, bandwidth of the filter reduces. Therefore, you are increasing power spectral density of noise, but you are reducing the bandwidth of the system. Therefore, it is expected to be independent of R, and effectively it will be, because both will cancel out each other. So, this part won't be there. Then therefore, higher C leads to less noise. So, this keeps this in mind. Now, what about other side? So, as long as this is a passive circuit and we don't have any problem with the breakdown, you can apply as high as possible. As long as resistor and voltage work, you can apply a voltage as high as possible. However, if voltage is limited because of other factors, for example, if you are working in a circuit in which you cannot go above VDD, therefore the maximum swing you can get for a simple, for example, sine wave is limited to VDD. Therefore, you will have a limitation from other side also. So therefore, if Vmax always is less than VDD, therefore this will give you a limitation for the higher side also. For example, if I have a sine wave in a particular frequency, operating frequency which is in the band, its RMS value is given by Vmax upon the square root 2. What is Vmax? It's better instead of Vmax use Va. And Va is amplitude. So this is RMS value of sine wave. Say for example you apply to the input of this RC filter. How much this can be? Maximum amplitude you can get is limited to VDD. And then if I have a single supply system, therefore VA max will be VDD by 2. Because I have a linear system, therefore my sine wave should be symmetrical. I cannot clip it from one side. Otherwise it's fully nonlinear. And to have this linear system, therefore I should have maximum amplitude limited to this value. Therefore now we will have a max and min for value of voltages which are practically can be used. Of course, there are cases like, for example, in a power amplifier, you are able to generate voltages above VDD, where we use inductors. So right now I don't consider that, but even in that case also, you have a limitation on the maximum voltage which exists in the circuit can operate with. Because there are other issues like power dissipation and thermal budget and stress on the device and other breakdown and other issues. So therefore, the first thing you need to consider in any sort of analog or mixed signal is to make sure that you are always within the limit when you design the circuit. And ignoring noise is only acceptable if you have really a very relaxed specification for the design. But for high performance design, always noise is an issue. Okay, so that's why the one thing which is very famous, factor of 2 is when you consider peak to peak. This is 2 VA. VA is only this amplitude. So question was, there is a factor 2 here, but because I have considered amplitude, 2 doesn't appear. If I consider peak to peak, then 2 will appear. So this leads us to consider dynamic range. Dynamic range doesn't have a unique definition. Here, dynamic range is defined as the range of voltage. Okay, therefore it will be ratio of maximum voltage to minimum voltage. Therefore, in the case of a simple RC circuit with a sine wave at the input, VDD by 2 square root 2 divided by RMS value of noise, KT by C. Ratio of maximum RMS value to minimum RMS value, square root KT by C. All of you are familiar with filters, therefore I don't need to explain for you what is filter, right? You are familiar with a stop band, pass band, right? Rejection band, stop band, transition band, attenuation. Okay, so I don't explain all of them, it is not required. Only one thing which is required to consider is in filters, a concept of phase delay and group delay. So therefore, first we explained concept of dynamic range, and now we just talk about the reason is because usually these two concepts are not covered properly. Just I want to give you an introduction because when you want to design the filter, then we need to be careful about these two, specifically the second one, because at least if I deal with a large value of voltage, I'm not so concerned about noise, at least for passive circuits, but group delay is something that always you should be careful about. So what is the concept? Suppose you have a filter and this filter receives a range of frequencies, so it has a limited, it should pass some frequencies, okay? It's not a single frequency. It should pass range of frequencies. So you have a signal which is in band of the filter. Therefore, it is supposed this filter to just transfer this signal. If it is an active filter, therefore it may amplify the signal also. However, suppose you have a radar system, suppose you have a speech processing system, okay? If you apply a filter to this system, so in this system, all frequency components which arrive at some particular time to the filter, they should leave the filter also at some particular time. In other words, all harmonics of this signal should be synchronous or synchronized with each other. Now suppose you have a signal which has the bandwidth of, for example, 20 megahertz, but components below 1 megahertz arrive at one time and components above 10 megahertz arrive in other time with some delay, or vice versa. They arrive earlier and others. So though system looks linear, right? It's perfectly linear because it just has a transfer function. So that's it. So it's linear. And in fact, if it is not linear, we cannot talk about transfer function. So it's linear. But practically you will see distortion. The reason is because system is not able to produce same delay for all of them. And that's the problem. That's why we should be careful about the concept of group delay. The same thing is valid about, for example, radar systems. See, in speech processing, if this happens, and you know there is a lot of filtering in speech processing. So if this happens, you will see a lot of distortion. So group delay is very important if you design a filter for speech processing, even digital filter. After all, digital filters are the counterpart of analog in digital. So same concept is valid for them. Similarly, in a radar system, if an object should be identified, so all frequency components should arrive at a particular time. It's not possible to, some of them arrive at some time and some of them arrive at another time. So then the whole identification will be faulty. So that's very important in many applications. We should have a proper group delay. And that's why this is the concept of group delay. Group means group of frequencies. And delay for group of frequency should be same. Therefore, group delay is important. So therefore, say for example, we have just a simple transfer function like that. Suppose I have hj omega is equal to k into 2 power minus j omega t0. Okay. So if I have such system and then I apply in time domain signal xt, at the output I will get t minus t0. So this creates only a delay. What is the characteristic of this system? Its magnitude of transfer function is constant, k. Its phase is a linear function of omega, right? So that's why it is called a linear phase system. So therefore, if you want to have a good group delay, this simple example says that you should try to keep phase as linear as possible. Phase of the transfer function of the system. Okay. So if it is linear, then it is much likely to get a delay which is almost same for all frequency components which are in band. So now, if it is not, because it is not possible to really design all filters with this characteristic. So what will happen? So in that case, we should define some sort of figure of merit for group delay when we want to design a filter. So therefore, in addition to magnitude characteristics, we should also talk about a figure of merit for phase characteristics. So therefore, now I write it in a general form. Okay, so this is a general form. Here you can see in the previous example what is phase minus omega t0, right? And what is pi omega upon omega? It's minus t0. In other words, in a linear phase system, phi omega upon omega is a constant value. Okay? So therefore, it seems that if I use phi omega by omega, for example, or d phi omega by d omega, I can get an appropriate figure of merit for phase delay and or group delay. Actually, group delay is usually used when I use d phi omega by d omega. And phase delay is used usually when I use phi omega by. Okay. So therefore we use this. Therefore we want to see that if I have a frequency, for example omega, I get a phase phi omega. Now if I apply omega plus delta omega, now what I will get? So I will get phi omega plus delta omega. We want to make this ratio to be as constant as possible in the bandwidth of the filter, passband of the filter. So therefore we define this and then we go with this definition of phi omega by omega, and then we'll see if the system is not linear, right? It's not linear phase, therefore we need to see how we can relate it to the phase characteristic of the system. So I just, because this is phi omega plus delta omega, I will use expansion around phi omega, first order only. Okay, and then considering 1 upon the omega plus delta omega, because delta omega we assume is very small, therefore it can be approximated by 1 upon omega into 1 minus delta omega by omega. These things you know. So therefore finally we will get some interesting relation which tell us like how this will be the phase linearity of the system. This is just by rearranging terms, you will get this. It will be good also you try once to get relations. I don't spend time to derive relations here, but they are easy to be derived. So this is group delay, what we call group delay. So you can calculate d phi omega over d omega for a range of frequencies, right? If it is constant for a range of frequency for passband, then you have a linear phase. If it is not, you always want to make it linear, therefore you want to make this to be a constant and be smooth, and this is phase. Okay, so what we want, if filter is completely linear phase, then means that these two are equal, and therefore means that this term will be 0, second term will be 0, only first term will remain. And that is the reason at any frequency ratio of phase upon omega is a constant value. However, difference between these two will lead to an information how far we are from linearity. So therefore what we want, at least we want try to make these two to be close to each other. Means that when you want to design a linear phase, you try to make d phi omega by d omega constant. And to do that, for example, you can consider this actually making d phi omega by d omega to be close to phi omega by omega. Okay, so therefore in fact these two concepts are the main concepts. One was this phase delay and group delay, and one is this dynamic range. So now, having this in mind, because then we can go and come back to the network synthesis theory. There are minimum phase transfer functions also that I will talk about them as we go to the concepts. Right, yeah. How accurate? Yeah, we will see. For example, there are different mathematical functions which are defined in the modern network synthesis theory. They have been developed actually by mathematicians, and they have different characteristics. For example, one of them is very sharp in the magnitude domain, but it is not good in the phase domain. One of them gives you a very nice linear characteristics, but it is not giving you a very sharp transition in the frequency domain. Actually, these polynomials always have trade-off with each other. So we will see in the, standard theory of filter design based on different standard mathematical polynomials. Always there is a trade-off between these two. And then it depends also on the order of filter. So what you want to do is that if it is d phi omega by d omega, and this is omega, so you want to make this almost to be constant, right? So usually it is like that, or it is like that. So, and this depends on the order of filter. Now in continuation we will see, for example, for some of the filters like Bessel filters, which are using Bessel functions, they get a very nice phase characteristics, but not magnitude characteristics. Or for example, you can have all-pass filters. Of course, we don't have ideal practical all-pass filters. But in all-pass filters, you can design filters which actually, it's like a delay element. Only it gives you a linear phase. It is possible to design. So we will see some of them. If you are talking about how accurate it is, it depends on the order of filter. It depends on the nature of mathematical function. Yeah. Mm-hmm. You mean error? So the question is, when we use this expansion, we are approximating. Maybe I should write it in the form of approximation. Mm-hmm. No, but because you mean which phase delay? You mean phi omega by omega? See, they have same units. So yeah. Okay. Yeah. See, I understand what you say. What you say is that because we are using first order, the error which is generated in this expansion itself actually may lead, I mean, if we want to make this relation almost constant, right? See, the point is that if you make this assumption correct, means that making difference between these two small, what does it mean? If you look at here, this exactly means that you are saying that the second order terms are very small. Because this says that d phi omega by d omega is almost phi omega by omega. That means that these two are same. If I know I have a system which is not linear phase, however, with a good approximation, it is close to a linear phase system. Therefore, this means that this relation is valid, or at least it's very small, so that I can ignore this term compared to this term. And this is same as saying that I have these two almost equal to each other. And this is same as saying that these second order terms are negligible. This is only valid for systems that I have designed to be linear phase. If they are not, definitely they are not. Means that this relation is not valid at all. So the second term will be, for example, a second order of derivative, right? And delta omega square. So, was it your question? See, if your system is not linear phase, but it is approximating a linear phase, why second order term should generate error? If second order term generates error, then it is not a good approximation of a linear phase. What does it mean? It means that second derivative is 0, right? If second derivative is 0, means that your system is very close to linear phase. Your phase is almost linear because as a function of omega, it can be explained as a constant phi plus a omega, right? Denominator of here? Okay, if there is error in the denominator of this expression, why do you think they are small? See, omega and phi omega may not be small, but delta omega is small. No, this is not valid for all types of filters. This is only valid for a filter with a good approximation of linear phase. If you have made a filter in which you cannot ignore second order, what does it mean? It means that you can write phi omega in the form of phi 0 plus a constant into omega. If you have made a filter in which you can write this relation, then you can write this. But if you have made a filter which has more than these terms, second order terms, then it's not a good linear filter, linear phase filter. And depends, of course, how much linearity you define. It defines how much you define your group delay as a function of omega. So this means this, and that means this. So this is what we want. If we are able to do this, therefore directly we reach to this relation. Means that if making this difference small, then we have made a good linear phase. It's not valid for all types of filters, not at all. That's why we have different types of filters. Some of them have good phase characteristics, some of them have good magnitude, and interestingly, it's very difficult to make both of them. This is not valid for all types of filters. This is only assumed if a linear phase transfer function is approximated. And delta omega is small, but omega is not necessarily small, and accordingly phi omega. So it is not something special. It is the same as any function. If you look at phi as a function, omega as a variable, I mean, this is just the first order expansion. What you may say that is at omega equal to 0, right? Here you I should mention this omega at omega not 0. That is also one point. But still at omega equal to 0, you can have this relation, right? So your phase will be phi 0, and then in other frequencies it will be k omega. And phi 0 can be 0, therefore this will be 0. Then actually the situation you are talking about will come to the picture. But still in that case also, still if this second term is good enough and is small, then still there won't be any problem. I don't see anywhere that it creates error in the calculation. Maybe you can give an example that if there is a good linear phase approximation, but still you will get a lot of error in the second term. I mean, conceptually these two cannot happen together. I don't know at what condition it might happen. Because I assume second order is negligible, but now I say that then second order will lead to error. Maybe you can give me an example at the end. Okay, just numerical. Okay. Okay, any other question? So now we can switch back to, oh, I tell you like a few things also because I thought you may not know. Do you know what is port? Okay. Port, if you have a network, port is defined as two terminals of which when current flows from one terminal into the network, will leave the same current, will leave the network at other terminal. Okay? So therefore, for example, this is I1, it will leave network N with the same current. So therefore, this is called a port. Okay, because this definitions are required to know. Then, do you know what is a reciprocal network? Okay. Do you know what are Z parameters, Y parameters, hybrid parameters? Okay. So a reciprocal network is a network in which, for example, Z12 is equal to Z21 or Y12 is equal to Y21. So this is called, these are properties of a reciprocal network. So if you have a single passive element, linear element, we are talking right now all about linear circuits. It is reciprocal in the nature. Okay? If you have a resistor and look at this resistor as a port, it is reciprocal. Similarly, a capacitor or inductor is reciprocal. And any network which is made of these reciprocal elements, again, is reciprocal. Okay? So this is one property. Then, do you know about Horvitz polynomials? Anybody? Okay. So, reciprocal network, concept of port. Okay. The third concept will be Horvitz polynomial. Okay. What is Horvitz polynomial? If all roots of this polynomial are in the left side of j omega axis, means real part of them is less than 0, it is called Horvitz polynomial. And modified Horvitz polynomial I show it. So sigma j omega. This is the plane for location of poles. Okay. So in modified Horvitz polynomial, so in Horvitz polynomial all are on the left side. In modified Horvitz polynomial, all roots are either left side or on j omega axis. So therefore, it can include roots on j omega axis. So it will include these two regions. And if they are on the j omega axis, they are simple. Simple means that they are of order 1, means multiplicity factor is 1. Means that you will have one root, for example, at j omega 1 and minus j omega 1. You don't have two roots at j omega 1 or minus j. Okay. So multiplicity factor for roots on the j omega axis is 1. That is called modified Hurwitz polynomial. Okay. So it would be very interesting to know that the person who actually developed the backbone of designing modern networks using passive components was Darlington, and he published in 1939 a paper. And then in 1961, Hazony published another paper which in fact expanded Darlington theory, and that led to today's, and still it is well established, modern network synthesis theory. So this was just the story. And okay, so then content will be, one is when we say that I want to synthesize a network, what we mean here from network is a network with only lossless components, means that inductor and capacitor, passive networks. So there are other ways also, we can use lossy components also, but theory is similar, therefore I just teach this one, and other ones you can just check from the textbooks, and because some of you even actually you may know it, therefore it will be only a review for you. So first, before starting how we can use lossless network to synthesize the transfer function, see, after all we want to design a filter, and designing filter means j omega or hs is given to us, and therefore we want to design this filter. So we should realize this hs. We realize this hs using passive components L and C, and then we will make a two-port. So there will be one input port and one will be output port. This input and output port will be terminated by resistors. One resistor will be output impedance of driving source, and one resistor will be, of course, load resistor. You may have resistor infinite also, you may have resistor 0 also. These are special cases. So we will talk about general case. So first of all, there are very well canonical forms of this RLC networks. If I remove R, then it will be lossless, which is LC and the concept of this lecture. And then these canonical forms, which are in the form of ladders, will be used for synthesis of passive filters. And then you can just, by several rules, convert this passive filter to an active filter. So therefore, here our example is LC networks. So what do we mean? Suppose you have an LC network like this, and then it is terminated by a load resistance R2. Output voltage is across R2. You have an input voltage source with the output impedance of R1. So this is an example of RLC network, because you have two resistors. But your your main network is just an LC network, because inside ladder you don't have any lossy component. So therefore you have this LC network as a lossless two-port. So now you know the meaning of port, terminated by load resistance R2. Okay. So essentially in an RLC network, what is properties of Zin? Zin is called a driving point impedance, the way I have shown. If you look at from input port of this LC network, whatever you see is called Zin or driving point impedance. So Zin is a positive real function for if network is made of RLC and all of them are passive components. with positive value, of course. Passive means positive value. They are not active components. So what do we mean from positive real function? Means that first, Zin is a rational function of S. If S is real, Zin is also real. If real part of S is greater than equal to 0, real part of Zin S also is greater than equal to 0. These properties are useful because then we can use them to realize Zin. If somehow I can convert problem of realizing a transfer function to realizing an input impedance, then the problem of design is solved, right? So I can have just conversion of, or realization of input impedance. Then filter design problem is done. So other property of Zin is order of numerator polynomial differs from order of denominator polynomial at most by 1. Okay. So for example, you can have S3 as the 3 as the order of numerator and S4 as the order of denominator, but you cannot have S3 upon S5. So order is at most, difference is 1. So for a positive real Zin, poles and zeros of Zin are placed on or on the left side of J omega. Imaginary poles are simple with positive real residues, and for all values of omega, of course, real part is positive. Actually, therefore, this means that this Zin will have polynomials in the numerator and denominator, which are eventually modified Horvitz polynomials. So, for example, this is a simple example of a ladder with a terminated resistor. So, you see the transfer function. As you see, Zin is a rational function of S. Order of denominator is 3. Order of numerator is 4. And poles, all poles can be shown, will have negative or 0 real parts. And this is meaningful because what does it mean? If poles have negative or real 0 real part, means that eventually your circuit is, if all of them are real, if all poles have negative real part, means that it is stable, and this will happen. If you make R2 infinite, then actually you will have all poles on the J omega axis. In that case, you will have a oscillatory system. So, you don't have any pole on the right side because these components are all passive components. Therefore, it is not possible to generate energy on without any external source. If a system is unstable, means that it is able to generate energy. There are components in the circuit which are able to, in fact, convert energy from one form to another and then increase the amplitude of the original noise which exists in the circuit. But if you have all components which are lossy or lossless, but they are not generating any new kind of energy from original noise, they cannot increase the amplitude because they are passive, they are not active, they are not able to increase power. Therefore, you cannot get any unstable situation in the circuit. That's why all poles are limited to J omega x.